This assessment imagines a hypothetical electrophilic addition reaction that is exothermic in its first step. Electrophilic addition reactions to alkenes are almost universally endothermic in the first step, but by considering one that's exothermic, we can see the role of the Hammond postulate that the Hammond postulate plays in the selectivity of those other electrophilic addition reactions. Now, in this case, the product of path A is a secondary carbocation. The product of path B is a tertiary carbocation. We know that the tertiary carbocation is more stable and by a significant amount. But if the reaction that forms those two carbocations is exothermic, how will the selectivity change? Well, let's look at a reaction coordinate diagram as a way of starting our thinking about the role that the Hammond postulate would play in this. Regardless of which path we're following, we're starting at the same spot because our alkene is going to react with this hypothetical X plus. And so those would be at the same energy. It's given that this reaction is exothermic, again, hypothetically, and we can finish at A, which is our secondary carbocation. We'll label that as A. Or we can finish at our tertiary carbocation, which we'll label as B. And now we note a significant difference here between the secondary carbocation and the tertiary carbocation, exactly what we would expect based on hyperconjugation. Now, given that this is an exothermic reaction, we can now connect the two, and we get something that looks like that for pathway A. We can draw pathway B in blue that would end up looking something like this. Now you'll notice that I intentionally have the two transition states really close to each other. Why is that? Because we don't know what the transition state looks like, but the Hammond postulate allows us to make a guess. And we can ask ourselves the question, is this transition state closer in energy to the reactant or closer in energy to the products? It's clear from the reaction coordinate diagram that this exothermic reaction, as all do, has a transition state that's closer in energy to the starting materials. Thus, regardless of which path we're following, path A or path B, these two transition states are pretty similar. If the transition states are similar, then the activation energies are similar, the reaction rates are similar, and the reaction would be non-selective. So exothermic reactions end up not being very selective because the transition states are reactant-like and therefore have identical activation energies. In the case of our truly, the true reactions where it's an endothermic first step, now those transition states are more product-like. That's why we see selectivity.